Hello everyone, as was said, I'm Daniel Luick, and I'm here to talk about ZKSMT, a virtual machine for proving SMT theorems in zero knowledge. This is joint work between researchers at Yale University, Galois, Boston University, and Northwestern. So just as a quick overview, this is a talk about verification tools that can prove code correct. Now, right now they can prove code correct to you, but if you wanted to be able to prove their correctness to a third party, you would have to give that third party a lot of details about, say, the source code or any details of the proof. This might not be ideal if the code is private, such as being proprietary. So what we want to do here is to be able to validate a crucial part of that tool chain while keeping some details private. So we all know that safety and reliability are important in software. Bugs in software can have a huge impact in widespread systems or safety critical systems. So because of this, we want a wide variety of approaches for mitigating bugs whenever they exist. And verification is one such task. So when done correctly, it'll ensure that your program is free of certain kinds of bugs. Now, verification can often be difficult, but there's a lot of tools that have been developed to try and make it as automated and straightforward as possible. A lot of these tools are based on SMT solvers, which are tools that can take logical formulas, a variety of logical formulas, and solve them automatically while scaling up to solve larger formulas and do it fairly efficiently. However, again, if you want to take all these tools and use them to demonstrate correctness to a third party, basically what you just have the third party do is run the whole tool chain themselves, which gives them access to things like the code. So what if then you have something like proprietary software? Now, just to show how this would work, let's walk through the pipeline for these things. So you start off with your source code and some sort of a specification saying no overflow errors, something like that. You run it through your program analysis tool, which will generate some number of formulas. And then next you want to solve them, so you run them through your SMT solver. One particular note is that you generally want to prove the generated formula is false, because usually they encode the question of, is there a bug in my code? And so if it's false, then there is no bug in my code. So if you're successful, you get some sort of a certificate which has the details about the proof. Then finally, you run this through an unsat checker, which is just a simple checker that goes through and makes sure all the rules of the logic were followed. So this is what our tool chain looks like. And again, what if we wanted to use this to demonstrate correctness to a third party? We essentially just have them run the tool chain, is what we would do right now. But if they want to do that, they need a lot of details. So they need to see this source code, this generated formula, and all the details of the proof. And this might be okay if your code is open source, but what if your code is proprietary? One particular case where this might be important is if you have, say, an app store. So app stores would very much like to verify security properties of any submitted apps, but the app developers might have proprietary code. This might be especially important because app store developers themselves often release apps, so you might start to have antitrust concerns. So is there a way we can sort of have the best of both worlds? So can we verify software to a third party while keeping that software proprietary? So what we want to do here is verify a specific part of that tool chain while keeping details private. So what ZKSMT does is it's able to take a formula and prove it false to a third party while keeping the generated formula and any of the details of the proof private. Specifically, we're able to work with formulas using Booleans, uninterpreted functions, and linear integer arithmetic. Although we design it in a way that it could most likely be easily extended to handle new theories fairly quickly. So I know this is a zero knowledge session, but just to make sure everyone's on the same page for zero knowledge proofs, the way you can think about them as it relates to this is, you have some sort of function f. You're interested in the question, is there an input x such that f of x equals 0? You have two parties, a prover and a verifier. The prover knows what x is, but wants to keep it private. The verifier is interested in being convinced that x exists, but wants to make sure the prover isn't cheating. So relating this to our pipeline, f is the whole, evaluating the whole pipeline. X is all of those details we wanted to keep private, and the verifier is the third party we want to convince of correctness. So before I go into what a zero knowledge version of checking this looks like, I just want to walk through what the plain text version of this looks like. So what does an unsat proof look like? So the sorts of conditions we might want to prove might look like this, this simple one I've been showing as an example, or they might look like this one, which is 4 megabytes of formulas output by a tool called Daphne, which this is what GitHub looks like when you try to open it. But just for a very simple toy example, let's look at x is less than 1 and x is greater than or equal to 1. So this is obviously false. Numbers cannot be less than, greater than, and equal to anything. But how do we go about proving it? So there's a number of formats that will do that. These are actually relatively recent work. They've been developed in the last few years, but most of them look something like this. So they have this list of steps, and at every step you have some sort of a conclusion, which is a formula that can be derived from your initial formula. You have some sort of a rule, so all these formats have some list of rules, which are the ways you're allowed to derive new formulas for old ones. And then if you are using an old formula, you have to list it as a premise and show where it was previously proven. So you'll note that the very first formula is always our initial assumption, and the last formula is false, because our goal here was to prove false. So going through this, we just have a number of our rules we might use. So for example, something like saying, if I know A and B, then I know A on its own. So just a way of manipulating Boolean statements. And then of course, because I had to show I knew A and B, I have to list that as a premise. I can use that again. I can use a rule such as arith sign for manipulating arithmetic inequality. So if I know x is greater than or equal to 1, then it is not the case that x is less than 1. So just flip the sign. Then I might have a rule like contradiction. So if I know A and I know not A, that's contradiction. So I have false. So this would then end our proof. So this is a plain text version of our proof, and we want to turn this into zero knowledge. So what are some of the difficulties here? One thing is if you look at all of these formulas, they might have different signs because they're defined as recursive data types, and they can just sort of be as large as you want. This is problematic because in zero knowledge, you can't really directly hide the size of data. You have to do it in some indirect way. So the next thing is that there is a relatively quick off-the-shelf solution you could use. So there are generic purpose ZKVMs that can take, say, any LLVM program and execute that directly in zero knowledge. So we could do this, but this leaves a lot of optimizations in the table, things like having a lookup table or some tricks we can do for specific rules. And we do care about efficiency. So what we do then, so our goal is for SMT proof checking, and the way we do that is that we check that table by sort of thinking of it as similar to program execution. So we develop a virtual machine. This is where the VM in our title comes from. And what we do then is we design it in a way that it can be efficiently compiled to zero knowledge. Our full architecture looks something like this. This is kind of complicated, but I'll walk through some parts. So again, we wanted to treat verifying this table as program execution in a virtual machine. So to continue this analogy, that would mean that each of these steps you see here is basically one instruction. So the premises correspond to operands of the instruction, the conclusion is the result, and the rule itself is the opcode. So in an assembly, you have things like load, store, addition, multiplication. Here you have rules like arith sign or contradiction or and usage. So a proof step is one instruction. Continuing on, so the equivalent of the control unit is our main checker, which is something that just walks through each step of the proof and checks it in turn. So it'll load any of the premises and conclusions that are necessary and dispatch them to a subchecker. So the subcheckers are like the ALU. So there's a little bit of code for each rule you might want to check. This is just often something like pattern matching. So for arith sign, for example, you just make sure that the premise and conclusion really are negated and they have the opposite arithmetic inequalities. Finally, we have a read-only memory. So I mentioned that we wanted to be able to hide the size of the recursive data structures. So the way we do that is that we take every expression that ever appears in the formula, we split it into its its nodes in its abstract syntax tree, and then we place all those nodes in a read-only memory. And what we do then is that instead of passing the entire formula around, we simply pass around pointers to the read-only memory. So this hides the size because all pointers have an equal size, and if we ever want to look into the expressions, we just dereference them. So for our evaluation, we do have a concrete evaluation. We have an artifact. We implemented this in EMP-ZK, which is a library for constructing interactive zero-knowledge protocols. We evaluated this on a benchmark suite on a bunch of Amazon machines. So a couple of highlights. One of the things we did was stress test it. So we ran it against some large proof examples from the official SMT lib benchmark repository. The largest test we passed had 200,000 steps, and it took about 3 hours. Larger tests than that ended up having out-of-memory errors. However, so this is as large as we can go for now, although we have some ideas how future work could improve on this. The next thing we did was compare with a generic ZK-VM. So as I alluded to earlier, one of our authors actually has a tool called cheesecloth that can execute any LLVM program in zero knowledge. So for a comparison, we took a bunch of benchmarks, we ran them in ZKSMT, and then we ran them by using a plain text version of our checker in cheesecloth. The goal here was to see if the work of sort of having the specialized protocol of ZKSMT was worth the cost. And it ended up being well worth the cost, so ZKSMT was always at least 1,000 times faster, and often even faster than that as well. So just to recap, ZKSMT enables private verification of SMT proofs. The way we do that is constructing a VM to check that table you saw in a way that can be easily compiled to run in zero knowledge. And it's fairly easy to customize to new theories, as all you would have to do is add more subcheckers. And brief advertisement, I am available for internships if anyone's interested. So that's all I have, and I'm happy to take questions.